Now let's look at the quantization of the Dirac field. Most of the time, we will be following the steps that we did when we were quantizing the scalar field. Now we have the Dirac Lagrangian, which we wrote as psi bar p slash minus m psi, where here p slash is actually minus I dash slash the operator. Del mu gamma mu plus I. And the Dirac field satisfies the equation p slash minus m psi is equal to 0. We search for the momentum state solutions, and we can expand this Dirac field using the Dirac spinors. We had discussed u and p as an integral over the possible momentum. We will use the normalization we also had in the case of the scalar fields. Then there are the coefficients, which will be the operators a k e to the power I kx. And these are the Heisenberg operators, so I just inserted time dependence also here. And there's the u. Let me insert also the s over here, and this ak also includes the index s. And then we have the other operators b k s dagger, e to the power I kx, and vs. And these are functions of k. Now, just for completeness, let me also write what these u's and v's were. U of s of k is square root of sigma p psi s, square root of sigma bar p psi s, and vs of k is sigma p psi s minus sigma bar p psi s. Now, before we only had the psi s, and now psi was a two-component spinor, and there are two independent ones. Conventionally, they will be chosen as 1, 0. This is psi 1, let's say, and psi 2 is equal to 0, 1. We don't really need the explicit form, but just for completeness. And so these are the two possible independent choices of psi s. For each choice there we have a coefficient a or b. Now, starting from this, let's first calculate. Now, we didn't look at the commutators yet, but let's look at the energy. Now, first we have to determine the momenta. Let's calculate the momenta corresponding to psi. Well, psi is a field, so it has psi is a spinor. It basically has 4 components. So for each component, we will have one canonical momenta. Momenta will also be a 4-component spinor-like object. And this the momentum is defined as the derivative of the Lagrangian with respect to the time derivative of the corresponding field. And this would give us psi bar I gamma 0 psi, which is just no psi gamma 0 k. This is just psi dagger of k. And if we were to look for the momentum corresponding to psi dagger, well, the Lagrangian we had written down doesn't have any psi k time derivative of psi k, so this will be basically 0. Time derivative of psi k dagger, so that is 0. So we have the Hamiltonian density I psi k dagger psi k dot minus the Lagrangian density psi bar I the 0 psi the 0 gamma 0 minus I gradient of psi. plus m. Now gradient of gradient at gamma psi is over here. Now note that this is just I psi dagger, psi bar, gamma 0 psi, time derivative of psi, minus psi bar, no, this is minus I dot 0 gamma 0 minus I gradient of gamma minus m psi. Now these cancel, so we end up having psi bar I dot gradient plus m. And using the equation of motion for psi, we can also write this as psi bar I dot 0 gamma 0 psi, or psi dagger I dot 0 psi. This is the Hamiltonian density. Now the energy of the system, which is the Hamiltonian, is just the integral d cubed x of the Hamiltonian density. Now we can just put the explicit expressions of this psi and psi dagger. This is equal to d cubed k, d cubed x. Now we have two momentum integrals, one for psi, one for psi dagger. So we have d cubed k1 divided by 2 pi cubed, square root of 2e k1, d cubed k2 divided by 2 pi cubed, 2e k2. Let's write psi dagger first. Psi dagger will be, it's this k1 integral, a of k1 dagger, u dagger k1 e to the power I k1x plus b k1. There's also summations over s and s prime, but I will be suppressing them. But just keep in mind that anything that has a momentum k1, there's also a sum over s. Anything that has a momentum k2, that also contains a summation over s prime. Anything meaning the operators and these u and v spinors. So let me continue writing it down. vk1 e to the power minus I k1 of x. Then we have the I del 0, the time derivative of, let me write the psi. Psi is contains the k2 momentum, so it will be ak2 u of k2 e to the power minus I k2 of x plus bk2 dagger v of k2 e to the power minus I k2 of x. Now let me, if I take this derivative, let me take the derivative, so this is equal to, I will also suppress the summation over s and s prime, d cubed x, d cubed k1 divided by square root of 2 pi cubed, square root of 2e k1, d cubed k2 divided by 2 pi cubed, square root of 2e k2. The first term just comes as it is. There's it's not taking, I'm not taking the derivative. There's no derivative to take. Now in the second term, this is a plus. In the second term, each derivative will bring a factor of minus I ek2. So let me just write ek2 over here. ak2 u of k2 e to the power minus I k2 of x minus, because here it will bring down a minus I ek2, which I took out, but in this term it will bring a plus I ek2, so there's a minus sign over here. Now, I will be multiplying these. Note that multiplying it out and taking the d cubed x integral, now the d cubed x integral will basically tell me that k1, 3 vector k1 should be equal to plus or minus 3 vector k2. So when I take the product of these two terms, in that product 3 vector k1 will be equal to 3 vector k2, but when I take this cross term, 3 vector k1 will be minus 3 vector k2. But in both cases, e of k1 will be e of k2 because it only depends on the square of the three vectors. And hence, I will just keep this in mind when I'm doing the computation. So let's see, I have this d cubed k1 divided by 2 pi cube, 2e k1, d cubed k2 divided by 2 pi cubed, 2e k2, and well, when I take the d cubed x integral, I will get some Dirac deltas with 2 pi cubed, so let me also write the 2 pi cubed out. Let me write ek2 over here. Now I have the products. A of k1 dagger, A of k2, u dagger k1, u of k2, Dirac delta, three-dimensional Dirac delta k1 minus k2. Well, note that here, since I'm in the Heisenberg picture, the k10 and k20 terms are also there, but I get e of k1 minus e of k2, which due to this Dirac delta, it will be automatically 0. So let me continue. This is the product of the first terms in the parentheses. Let me take the product of the second terms in the parentheses, so it will be similar here, but this time I have, here there is the dagger, minus bk1, bk2 dagger, v dagger k1, v of k2, Dirac delta cube, k1 minus k2. So this is the product of these two terms. Now let me look at the cross terms. The cross terms, let me write the first one, this term multiplied with this one, so it's a minus a k1 dagger, u plus k1, v of k2, then I have bk2 dagger, and then I have the Dirac delta cubed k1 plus k2, and then I have e to power I ek1 plus ek2 of t, and then I will be looking at this cross term, so it will be similar, so minus, no, it's plus bk1, bk2, no, ak2, v dagger k1, u of k2, Dirac delta cubed, k1 plus k2, e to power minus I e of k1 plus e of k2 of t. So these are the terms I have. Let me take the k2 integral now. Now, since I already know that in all of these, due to all of these Dirac deltas, e of k1 and e of k2 will be the same. So let me just first cancel these ones. I will get, let me just say d cubed k divided by 2 pi cubed. There is a 1 over 2 ek, the product of this one and this one. Let me for the time being still keep this e of k. Then we get a of k1 dagger, a of k1, u dagger of k1, u of k1, no, k. I just renamed k1 to k. And this Dirac delta just tells me that K1 and K2 are equal, so that's why the arguments over here are just K. And then we have minus V of K, V dagger of K, V dagger of K, V of K. And then I have these terms. In these terms, since I'm taking the K2 integral, K2 just becomes minus K1. So I have a dagger minus a dagger K, V of minus K dagger, U dagger of K, V of minus K, e to the power 2I ek of t plus bk a of minus k, v dagger of k, u of minus k, e to the power minus 2I ek of t. Well, here we have the products of Dirac spinors in these terms. We had already calculated these two. So u dagger of k, u of k is actually 2ek, and v dagger of k, v of k is also 2ek. Now we didn't calculate these, but you can go ahead and calculate them, and you will see that u dagger of k and v of minus k, this is equal to 0. V dagger of k, u of minus k, this is also 0. So this I leave to you as a homework. So these terms are 0, these last two terms. And these two terms, this and this, they are the same. They will cancel this 2ek. So we end up having the Hamiltonian of the system as d cubed k divided by 2 pi cubed ek, ak dagger ak minus bk, bk dagger. And in fact, you can go ahead and calculate the energy momentum operator, P mu, will be just d cubed k divided by 2 pi cubed P mu ak dagger ak minus bk, bk dagger. And this is your second homework to actually show this relation. No, not P mu, K mu. Well, if we would just continue with what we had done in the case of the scalar fields, we are in deep trouble here. Now, the problem here is this sign over here. There is the minus sign. Remember, in the case of the scalar fields, when we studied these are the daggers here. We impose commutation relations. So the commutation, if we impose the same commutations here, this bk, bk dagger would be just bk dagger, bk plus some number with a minus sign. So the Hamiltonian would be d cubed k divided by 2 pi cubed ek, ak dagger ak minus bk dagger ek plus some constant. Now the problem here is, due to this minus sign over here, by creating more and more b particles, the system can just lower its energy. The energy of the system is not bound from below, which just cannot be. So we have to resolve this issue. Now the way out is actually by saying that, by postulating that when we are quantizing the Dirac field, we won't be using the commutation relations, but we will be using the anti-commutation relations. So if you remember, in the case of the the classical field, the scalar field, we said that the field and the corresponding momentum at equal times, they satisfy the commutation relation. Well, let me just use different labels. Since we have more than one field here, this is Kronecker delta ik and the Dirac delta x, three-dimensional Dirac delta of x minus y. And this leads to the commutation relation between the corresponding operators. Now, in this case, it just doesn't work. So what we should do is the difference compared to the scalar field is we have to impose the, now there is also the I. We will be imposing the anti-commutation relations between these two. So this is minus I. So using these anti-commutation relations, you can actually show that the A field satisfies also the anti-commutation relations AK prime dagger is BK prime dagger. These are 2 pi cube, the three-dimensional Dirac delta of k minus k prime, and AK prime BK prime and AK BK prime. All these anti-commutators are 0. So these anti-commutator of two operators is just AB plus BA. Now when we quantize the system using this anti-commutator quantization condition, this is our quantization condition. In that case, the Hamiltonian, the total energy of the system, which is written in this form, becomes, when we use the anti-commutator, plus this number. So the energy is now bounded from below. Now, of course, this anti-commutation relation just has other consequences. For example, BK, since BK dagger, this is 0. This tells us that BK dagger squared is 0. Let me also put the S over here. This is also 0. So the creation operator acting twice, the same creation operator acting twice, gives us 0. But remember how we define the particle states. The particle states were defined up to normalization as BK S dagger acting on vacuum, where the vacuum is still defined as AKS acting on vacuum. This is 0, and BKS acting on vacuum. This is 0. The annihilation operator still annihilates the vacuum. Then we have this creation operator acting on the vacuum once, gives us a single state particle. If we want to have two particles of same momentum and spin, well, this is also 0, because this would be just BKS squared acting on vacuum, which is just 0. So this tells us that we cannot have two particles having the same momentum and spin. In fact, momentum and spin are just some quantum numbers we could have chosen to quantize the system using some other quantum numbers. And even if we do that, the system, we wouldn't be able to create two fermions at the same state. So this is just one demonstration of the simple fact that half integer spin particles well, we will see in the future videos that these Dirac fields describe particles with spin 1/2, but even if we have other higher half integer spin particles, the problem will be more or less the same, so we quantize imposing anti-commutation relation and integer spin particles are quantized imposing the commutation relation. This is the spin statistic theorem of field theory. And if you trace the problem over here, you see it's essentially due to the fact that there is a sign difference between these two terms, whereas there is no sign difference over here. Now the sign difference, there's sign difference between these two terms, mainly because here we have the first derivative. In the Hamiltonian, we only have a single time derivative. So this is the origin of this commutation relation. The fields of half integer spin particles, just like the Dirac field, will satisfy equations similar to the Dirac equation with a single time derivative, whereas integer spin particles will satisfy a Klein-Gordon-like equation with two second order time derivatives. And when you have a second order time derivatives, there are no such relative sign mistakes. So that is why all half integer spin particles satisfy have anti-commutation relations, where integer spin particles have commutation relations. Now, anti-commutation relations also tells us that the corresponding wave functions are anti-symmetric. So you see, let's say that we have one particle in the state K1s, the other particle in the state K2s. So this can be created up to a normalization as first let's create the K2s, then K1s. We are just fixing the notation. So if they satisfy anti-commutation relations, and hence this is equal to, if since this is non-zero K1 and K2, they are different, or S and S prime are different. So this is minus K2 S prime P of K1 S daggers. But this is K2 S prime K1s with a minus sign. So when I exchange the states of the particle, when I exchange the quantum numbers of the first and the second particle, that is when I exchange the particles themselves, and then the state acquires a minus sign. And hence the wave function of these fermion Dirac particles should be anti-symmetric.